Hi everyone, in this video I'm going to go through the solutions to the worksheet on 6.4, Applications of Vector Addition. Alright, so let's start with question 1a. Determine the resultant of the vector sum, 54 kilometers west and then 23 kilometers per hour south. So 54 kilometers per hour west and then 23 kilometers per hour south. These two vectors form 90 degrees. So the resultant is going to look a little something like this. Let's get the magnitude of the resultant first. We can just use the Pythagorean Theorem since this basically forms a right angle triangle. So the square root of 54 squared plus 23 squared is approximately 58.69. Next up, we can use the tangent ratio to get this angle right here. Then we can find the bearing. So theta is just the inverse tangent of 23 over 54, which is around 23.1 degrees. Now from the true north line, if this is 23.1 degrees, this would be 90 minus 23.1 degrees, right? 90 degrees minus 23.1 degrees, that's 66.9 degrees. So if this angle from due south to here is 66.9 degrees, then the bearing would be south 66.9 degrees west, right? And our magnitude is 58.69 kilometers per hour. Right. B. All right, next up we have 120 meters per second west and then 75 meters per second east. All right, west and east are opposite vectors, right? Here is 120 meters per second, or just 120, and then here is 75 meters per second, right? So since the vector going west is bigger, our resultant is still going to be west, right? That right here is a resultant, which is found by just subtracting the two, right? That's going to give me 45, right? So the resultant is just 45 meters per second west. All right, and then we have 1e, determine this resultant. All right, so here we're going north 45 degrees east, 90 kilometers. Okay. And then 54 kilometers south, 30 degrees east. So from south we go 30 degrees east, so this is 30 degrees right here. This is 54. So our resultant is going to look a little something like this. All right, so we have to find out what this angle is right here, right? And if you recall your angle properties, we have alternate angles right here. So if this is 45 degrees, so is this. So this right here is also 45 degrees, which means this whole angle right here, this whole angle would be 75 degrees, right? 45 plus 30. So we can use the cosine law to solve for the magnitude of the resultant. Got 90 squared plus 54 squared minus 2 times 90 times 54 cosine of 75 degrees, which is approximately 8,500.28. That's the magnitude squared, so the magnitude is just the square root of that. Okay, and that's around 92.2. Now for our bearing, we can find this angle right here. Let's call it beta. So we can use the sine law, right? Sine beta over its opposite side, which is 54, is equal to sine 75 over its opposite side, the resultant, which is 92.2. So sine beta is equal to 54 sine 75 over 92.2, which is approximately 0.57. So beta would just be the inverse sine of that, right? 0.57, which is around 34.5 degrees. So if that's 34.5 degrees, then we got to get the whole bearing right here, right? This whole bearing right here. Okay, so the bearing is just 34.5 degrees plus 45 degrees, which is 79.5 degrees. So that means our resultant is 92.2 kilometers at a bearing of north 79.5 degrees east. 2. Find the magnitude of the resultant of the four forces. Now this looks a little bit tricky at first, but it's really quite simple. We just have to resolve the two pairs of opposite vectors, the ones going up and down and the ones going left and right. So up and down we have 16 newtons, and then we're going to go down 7 newtons, right? So our resultant is still going to be up, right? Because our upwards vector is bigger. Okay, so our resultant here is 9, right? Going up. Next up, we have the vector going left, and then a smaller vector going right, right? So our resultant is still going to end up being left. 23 minus 11, that's 12, right? Okay. So what we can do now is we can just add the two resultants of the sums of the opposite vectors and then just use the Pythagorean theorem. Alright, so we got 12 going this way, 9 going up this way, and this right here would be the resultant. So the resultant is just 9 squared plus 12 squared, and you get the square root of that, which is going to give you 15. And we can use the tangent ratio. Okay, of 9 over 12, which is going to give you 36.9 degrees. This means the bearing, okay, if this is if we're doing north, south, east, west, this right here would be 90 degrees minus 36.9 degrees, right? Which is 53.1 degrees. So our resultant is 15 newtons at a bearing of north 53.1 degrees west. 5. A sine weighing 98 newtons is suspended from the middle of a 4-meter long chain. The ends of the chain are attached to a ceiling at points 3 meters apart. Determine the tensions of the chains. Alright, so the tricky part here is trying to get to the diagram. Okay, so the ceiling, okay, the ends of the chains and the ceiling, which is the top, is 3 meters, right? And the middle of a 4-meter long chain is where the sine hangs, right? So if it's hanging from the middle, these two must be the same length, right? And it's 4 meters. So each of these two sides will be 2 meters, right? We can call these the tension vectors, T2 and T1. Okay, they're going this way. All right. Now, the lengths here will help us solve for the angles. Once we solve for the angles, we can redraw the tension vectors to find the opposite vector and solve for the tensions of the chains. Okay, so what we have to do first is to use the side lengths to solve for the angles. And we can do that by using the cosine law, right? If we were to call this angle theta, now these two angles would be the same, right? Because we have an isosceles triangle, so the base angles are the same. So cosine of theta, for those who remember the cosine law, is 3 squared plus 2 squared minus 2 squared over 2 times 2 times 3. That's 9 over 12. And the inverse cosine of 9 over 12 is going to give us theta, which is approximately 41.4 degrees. Okay, so now that we know it's 41.4 degrees, I'm going to redraw the tension vectors. Okay, I'm going to move the second tension vector up here. Okay, so using our alternate angles, if both of these are 41.4 degrees, then this whole sum, this whole angle would be 2 times of that, right? It'll be 81.8 degrees. And when these two are added up, it'll give us the opposite vector to the sine, right? Okay, so this is also 98 newtons. All right, so now that we have that, we can solve for the tension of the two the tensions of the chains, right? The tension vectors in terms of newtons. which should be the same because they're the same length. So T1 and T2 should be the same. So the magnitude of the two vectors are equal, right? And we can find them. Magnitude of T1 over sine of the opposite angle. Remember, we still have an isosceles triangle, so these two angles should be the same, right? This would be 180 degrees minus 81.8 over 2, right? Because there are two of those base angles. Oh, sorry, I made a mistake here. This should be 82.8. I did not multiply that correctly. My mistake. So I still have to subtract 82.8, and that should give me 48.6 degrees. Okay, so T1 over, so these two angles right here, over sine 48.6 degrees is equal to 98 over its opposite angle, which is sine 82.8 degrees. So T1 is therefore equal to 98 sine 48.6 degrees all over 82.8 degrees, which is approximately 74.1 newtons. Okay, so now that we have their magnitude, we more or less know their bearings too, right? Their angles, right? Because these are angle properties. These angles right here would be theta, right? So they're both 41.4 degrees from the horizontal, depending on whether you're looking at from the left or right. Okay. All right, that concludes number 5. Let's look at number 6 now. A community center plans to install a new basketball hoop on the side of the building. The hoop and backboard have a combined weight of 196 newtons and are supported by a brace and a wire. Determine the tensions in the wire and the brace. Okay, so we can look at it this way. T1, the vector is like this. T2 is like this, right? And combined, okay, they will form this resultant vector over here, which is 196 newtons. Okay, so sorry, T2 should look more like that. Okay, so we can just use cosine to solve for T1, right? So cosine, because we know this adjacent relative to 15-degree angle, okay? Here's the adjacent side, and this is right here would be the hypotenuse. So cosine 15 is equal to adjacent over hypotenuse, which is 196 over the magnitude of T1. So T1 is 196 over cosine 15 degrees, which gives me approximately 202.91 newtons. Okay. T2, on the other hand, we can use the tangent ratio relative to the 15-degree angle, right? Because we have the opposite and the adjacent right here. So that's T2 over 196 is tangent 15. So T2, its magnitude, is 196 times tan 15, which is approximately 52.52 newtons. All right, and that concludes question 6. Lastly, question 8. A sailor wishes to sail to a port that is located south 82.5, not south, sorry. Well, south 25 degrees east of his present position. The average speed of sailboat is 23 knots, and the wind is blowing from north 85 degrees east at 12 knots. Draw a vector diagram of the situation. Okay, so let's draw the vectors first. So the wind is blowing from north 85 degrees east. That means it's going this way, okay? Because it's from north 85 degrees east. And what else do we have? We have okay, so we have the speed of the sailboat. Okay, so this is the wind. This is the wind right here. And then we have the sailboat going this way. Okay, that's the sailboat. And when I add those two, it should take me south 25 degrees east. Okay, which is where I'm trying to go, right? So this right here is 25 degrees. All right, so we can use this information to solve for the direction of the sailor, okay, and the ground speed. So this is 12, and this is 23. So what we can do first is we can solve for some angles here. So we're trying to find the direction in which this the sailor should sail, right? Let's call this angle beta. And this right here should be 85 degrees because of opposite angles, right? So this whole angle, this is 110 degrees. Okay, that angle right there. All right, so this angle, let's call this angle over here theta. Okay, so we can solve for theta by using the sine law, right? Sine theta, opposite of its known side, which is 12, is equal to sine 110 over 23. So sine theta is equal to 12 sine 110 over 23, which is approximately 0.49. And if we got the inverse sine of 0.49, we get 29.3 degrees. So this is around 29.3 degrees. And I can just solve for beta by using the angle sum of triangles property. I'm going to take 180 degrees, I'm going to subtract 110 and 29.3, which is going to give me 40.7 degrees. So if this angle beta is 40.7 degrees, then that must mean that this angle right here, okay, now this angle right here should be equal to, this angle right here is also equal to 85 degrees, right? Because we have corresponding angles here and here, right? So the bearing is 85 degrees plus 40.7. Okay, so the bearing is 85 degrees plus 40.7 degrees, which is 125.7 degrees. Or if you want to be more exact, north 125.7 degrees east. Okay. C, what will the sailboat's ground speed be? So now we've got to solve for this. Let's call it vector S. Okay. So the magnitude of vector S, we can just use the cosine law now, right? Since we know angle beta and the two vectors in between, 12 squared plus 23 squared minus 2 times 12 times 23 times the cosine of beta, which is 40.7 degrees. Okay, that gives me approximately 254.51. That's the magnitude of S squared. So magnitude of S is the square root of that, which is around 5.95. It's a speed, so it should be kilometers per hour. Or maybe not kilometers per hour, maybe knots. We gotta use the same unit. All right. Okay, and that concludes question 8.